Combination circuits. In this presentation, we're going to take a look at two different styles of combination circuits and how we solve them. Now, both these types of circuits examples we're going to look at rely upon Kirchhoff's current law and Kirchhoff's voltage law. You need to have a general understanding of how they would be applied. If we look at Kirchhoff's current law, it simply means that the current in equals the current out of a circuit. So if we have this one here, 8 amps entering into this whole structure, then we can safely assume that 8 amps must also be leaving. Now, taking that a little further, if 8 amps meets this junction and only 3 are traveling to the right, then that would mean logically 8 minus 3 would give me 5 amps that must be traveling through this lower section. And to take it all the way, if 5 amps are then entering this junction and 2 amps are flowing down here, then that must mean 5 minus 2 giving me 3 amps traveling in this branch. If we then add all of the current values here, here, and here, we should again reach our 8 amps worth of current. So Kirchhoff's current law is a helpful item to remember when calculating combination circuits. The other one that we run into is Kirchhoff's voltage law. Now there's a number of different ways that we can explain, define, or describe Kirchhoff's voltage law. It has to do with the voltages in a closed loop. And although the equation would then tell us that all the voltage rise and drop if we were to add them all together should equal 0, an easier method to apply this is by looking at series versus parallel connections. In this circuit, we have 20 volts across this resistor and 30 volts across this one. Now remember, if there's 30 volts from here to here, that must also mean that there is 30 volts from here to here. And if that's true, then this voltage plus this voltage should equal 30 volts. Now we're drawing this conclusion based on the voltages inside a closed loop. This voltage should be equivalent to the voltage of the 5 volts plus whatever the mystery one is. So in order to work out the voltage of our mystery resistor, we would take 30 and subtract 5. 30 minus 5 gives me 25 volts. Now, what about these two remaining resistors right here? What if we were to add another piece of information? Let's say they are the same ohmic value. Let's say these two resistors, resistor 1 and resistor 2, are exactly the same ohmic value. What would that mean? Well, we could work out the voltage, because if they're exactly the same ohmic value, it would mean that they have exactly the same voltage. And the reason they'd have the same voltage is because the current that flows through them would be the identical value of current. So if 5 volts is present from here to here, it must also be present from here to here. And if they have to be identical in value, we take the 5 volts and divide it by 2. So that would be 2.5 volts each. Now that we know all of the voltages, we could also solve for the total source voltage. Because remember, this would have to be connected to some sort of source. And let's say the source is over here. What size is the source voltage-wise? Well, the voltage of the source will have to be equivalent to all of the voltages added up along a series connection. We're not going to add them up here. Rather, we're going to add them up across. So 25 plus 5, we already know is 30, plus another 20 volts would tell me that the source is actually 50 volts. So we can use Kirchhoff's current law and Kirchhoff's voltage law to calculate and solve missing values within a combination circuit. Let's take this one, for instance. We've got a number of ohmic values voltage, and current. Well, the easiest thing for us to do initially would be to transfer some information that we know to be true to the different relevant portions of the circuit. So if there's 10 amps here, it's safe to assume that there is 10 amps on this side. If there's 15 volts here, it's safe to assume that there is 15 volts across the 4 amp resistor. So there would be 15 volts here. At this point, we've got a few places where we've got quite a bit of information. So let's start calculating out the values. Well, 10 amps and 3 ohms. We're going to be using our Ohm's law for most of these calculations, and we know that I is equal to E over ohm. E is equal to I times ohm, and R is equal to E over I. So if we wanted to calculate the voltage, 10 times 3 would give me 30 volts. If we wanted to know the current value through the resistor on the far left-hand side, we would take 10 and minus 4 from it, which would give us 6 amps. Now remember, 10 amps is flowing out from this direction, which would then mean that 8 amps traveling up here, once it reaches this connection point, must combine with another 2 amps that must be flowing through this upper section. 8 plus 2 equals 10. Now, if we know what the 12 ohm and 2 amps is, and I'm going to add another ohmic value in here, I think that was missing from the beginning. So let's say that we have here, let's say 1 ohm. There we go. So if we know that the current flowing through these two is 2 amps, then we can use Ohm's law, I times R. So 2 times 12 would give me 24 volts. And 2 times 1 would give me 2 volts. We already know that there's 15 volts present here, which means now we can solve for the remaining items. What about the voltage across this resistor here? Well, we've got a 24 and a 2 volt. So that means if we add them together, we should get the total voltage across this resistor, which should be 26 volts. The total current of this circuit is really already provided for us. It's 10 amps. The total source voltage is going to be a sum of all the voltages moving along horizontally all the series connections. We're never going to add these voltages together because remember, in parallel, the voltage is the same. We are not looking to add voltages. So 15 plus 24 plus 2 plus 30 gives me a source voltage of 71 volts. Well, let's see if we can then apply this logic to a slightly more involved question, or perhaps a different type of question. What we're going to look at now is calculating all the voltage and current values in a combo circuit, but in a slightly different form. So let's take a look at what that form is. So what we're going to be doing is calculating values for something like this. We want to calculate all of the current and voltage values for each resistor, but all we're given is ohms. And so the method that we've just looked at on the previous example is not going to apply here. We can't use it. We need more data in order to calculate all the missing values. So there's some steps that we need to keep in mind, and the steps are quite simple. First, we need to calculate what the total resistance is of the circuit. As in, if I were to replace this source with an ohm meter, what would the ohm meter read? The second thing we then need to do is calculate what the total current is. And that's just by using Ohm's law. Finally, once we know that, we are going to spend a little bit of time then calculating each of the individual voltage and amperage values of each of those resistors. So let's start off with the first step. And the first step, as we just said, was to calculate our total. Now, in order to calculate our total, it's usually beneficial to resketch the diagram so that it represents a left to right type of schematic, something like this. We've got our connection from the positive side of the source going into a 3 ohm resistor. Out of the 3 ohm resistor, we can see that it branches. There are in fact 2 resistors that connect, a 6 and 5 ohm. The 2 then connect back together to an 8 ohm, which we see over here, and the 8 ohm then travels back to the source. Now, to calculate the total resistance of the circuit, what we have to do is apply our series and our parallel rules. So, series rule for R would be R total is equal to R1 plus R2 plus R3. That would be for series. Now, for parallel is a little different, right? R total is equal to bracket R1 negative 1 plus R2 negative 1 plus R3 negative 1 close bracket negative 1, and this would be parallel. So we need to keep that in mind as we calculate the total value. Now, often this is referred to as breaking the circuit down to a simplified form, and what we have to do is observe and identify which resistors are in parallel, which resistors are in series. The two that most jump out to me are the 6 and 5 ohm. Those two are in parallel, and what that means is that we are going to combine these two in parallel and determine what is the total ohms of resistance that these two represent. Once we do that, we can then represent that as a single resistance. And in doing this process, we then simplify the circuit. So notice that the 3 and the 8 ohm resistors have remained in place. They didn't get changed at all, but instead I combined the 6 and 5 in parallel using my parallel resistance formula, and I got 2.72 ohms. So this would be an example of reducing this circuit one step at a time. Next step, I want to calculate this so that it is a single chunk of equivalent resistance. And that then requires me to combine all of these in either series or parallel. And we can see quite obviously that these resistors are connected in series, which then means that if I simply add them together, 3 plus 2.72 plus 8, we should get the total resistance of the circuit. That gives me 13.72 ohms. Well, 13.72 ohms. So that's the first step that we need to take in order to calculate all of the voltages and currents. The second step is now going to take us into calculating the total current and the voltages. So let's head off to that. So the first step we want to do is calculate I total. Well, this should be fairly simple because I total and an R total here, well, let's write out our Ohm's law. I is equal to E over ohm. E is equal to I times ohm. And R is equal to E over I. So if we know that it's 13.72 ohms, that's the total resistance of this entire circuit, and the source voltage is 100 volts, then all we need to do is apply Ohm's law. 100 divided by 13.72 gives me a total current value of 7.28 amps. Now, it's important to understand that decimals will be important. I'm only going to carry 2 decimals up. for each one of my calculations. So at this point, we've got one value of current. This is my total calculated current, I total. What do we next do? Well, we now have to calculate all of the individual voltages and currents. Well, how do we do that? Well, I would say first, let's fill out all the information for this lowest single chunk of resistance. What's the voltage across it? Well, it's actually 100 volts. So we've got 100 volts, 7.28 amps. And now what we do is we imagine this like a rung on a ladder, and we move to the next rung up. And we identify what has moved, what has changed, and what can I take with me to this available step. So the 13.72 is actually calculated by adding these all in series. 100 volts would be from here all the way to here. So although that would be true, it's not really functional or helpful for me to transfer it. However, the current of 7.28 amps, the current should be the same here, 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 and here. And to just make this process a little bit cleaner, I'm only going to place it in one spot, 7.28 amps. So now that I've transferred some information, I'm now going to look at what I can calculate with that information. And again, Ohm's law is used. I'm going to calculate the voltages. E is equal to I times R. So I'm going to take my current of 7.28 and I'm going to multiply it by 8 amps. Gives me 58.24 volts. I'm then going to take my 7.28 amps and multiply it by 2.72. I get 19.8 volts. And finally, I'm going to take my 7.28 and multiply it by 3. And I get 21.84 volts. At this point, I have now calculated everything on this rung of the ladder diagram. I'm now going to go from this rung to the top rung, or the original circuit. And at this point, again, we're going to find that there's a substantial amount of information that we can take with us to complete this question. So first I'm going to look at what things have not changed. Well, it looks like the 8 ohm resistor is the same. And so I'm going to put the voltage up there, 58.24 volts. And the 3 ohm resistor has not changed. So I'm going to put the 21.84 volts. What about the current values? Well, the current value of 7.28 amps should still be the same. As we see, the 8 ohm resistor has not changed. And remember, it's a series circuit, so that would also mean that the 3 ohm resistor has the exact amount of current. So 7.28 amps and 7.28 amps. Finally, we look at the middle section. The middle section is right here, 19.8 volts from this point to this point. And if we slide this up, we'll see that those 2 points still exist. It's the voltage between the 3 and the 8 ohm resistor. So that would mean that 19.8 volts is present across both the 6 ohm resistor and the 5 ohm resistor. Now that we've transferred all of the information up that we can do our final calculations. 19.8 ohm or 19.8 volts and 6 ohms, we can use Ohm's law to calculate the value of current through each one of those individual resistors. So 19.8 divided by 6, 19.8 divided by 6 gives me 3.3 amps. 19.8 divided by 5 gives me 3.96 amps. And so finally, we can go back to the original diagram and fill out all of the information for each one of those resistors. We have 7.28 amps, present in two places, which makes sense. Whatever current goes out must come back. We have a current value of 3.3 traveling through the 6 ohm resistor, and a current value of 3.96 through the 5 ohm resistor. Finally, the voltages across each one of those individual resistors, 21.84 volts. Across the parallel branch is 19.8 volts. And finally, the lower portion with the 8 ohm resistor is 58.24. When calculating these types of questions, it's important to keep intense organization. If you do not organize your values, it's highly unlikely that you are going to come to the correct answers at the end, as there are a number of steps that we must take in order to calculate the missing values.